right, so thank you everyone for joining us today. Our topic this morning is, HSE benefits of microfluidics, smaller samples, safer solutions. And our speakers today are Cara Fan, a laboratory technician for interface, and David O'Brien, mechanical engineering team lead.
Thanks, Lee. I will start covering some of the benefits that interfaces technology bring in the aspect of sample handling and storage. So at Interface, we're performing fluid property tests on microfluidic device. These devices consist of a network of micron or nanometer scale channels where we can modify the channel size, geometry, and wettability to achieve a variety of testing conditions. This type of setup gives us the advantage of gaining both numeric and visual data with short amount of time. And most importantly, we're able to perform precise and accurate measurements with significantly less smaller amount of time with very small sample size, comparing to conventional fluid testing systems. To be more specific, using minimum miscibility point MMP measurements as an example, Interfaces technology requires less than 5 milliliter of live oil sample per data point, and we're able to generate over 40 data points in less than 4 days. This diagram to the right of the page depicted a high-level summary of the results of one MMP test. Each data point shown as circles represent one run. Blue color indicates the admissible runs, and red color indicate the miscible ones. The y-axis is percentage oil displacement. It's a parameter we measured used to determine the miscibility of the gas and live oil samples. The x-axis shows the pressure at which the run was performed at. As you can see, we're able to scan through a range of pressure and pinpoint the MMP of the combination of sample and through many repeats and validations. Going through the whole process of the live sample prepping, for example, conditioning, subsampling, testing, and repeating. In total, our system requires around 50 mils of samples versus in traditional MMP devices. Usually, each run or data points requires more than 100 mils of live oil sample. With the small sample size we have comes with benefits in health and safety aspects of the operators. For example, using my own experience, when we're switching between different samples, we need to clean our experimental setups with toluene, which is a very toxic and carcinogenic solvent. Usually to clean up our system, 10 to 20 mils of toluene is more than enough. Not to mention that we're able to do this underneath a carbon suction filter or inside the film hood because how small our setup is. In comparison, if we're dealing with big apparatus of a traditional MMP device, we'll need to use a few magnitude more volume of similar solvents, risking long-term exposure of hazardous chemical. The same ideas goes to other sample handling processes such as collection, shipping, and waste disposal. In addition to the safety of operators, the small sample size also provide environmental benefits. As mentioned previously, one MMP test only requires around 50 mils of live oil sample, whereas conventional MMP measurements use a few liters. The carbon footprint came with the shipping of such different sample size. The container which required will greatly differ. To resonate with the previous slide, the environmental impact of sample and waste disposal is also significantly reduced. Looking ahead, Interface is working on bringing our hardware to facilities around the world, further reducing the environmental implications of testing. To the conclusion, all of these aspects of benefits will be beneficial to our clients in the way of more convenient and cost-effective sample collection and shipping. Most importantly, we're able to provide more data points with great precision and accuracy with less sample required. Here's some more example of our fluid testing systems. So the two examples shown down here, instead of measuring fluid property, we're measuring how the flow pattern change in the presence or absence of chemical reagents. To the right, this picture really illustrates how small our microfluidic device is using the microscope lens as a reference. So under the lens here is one of our enhanced oil recovery design, which we use to screen for chemical reagents. And the video to the left shows our flowback processes. So this chip here is essentially a reservoir analog. These tight network of nanochannels with some pore scattering around kind of imitate the very tight shale rock formation, and the triangle to the left is imitate the frac end of each frac zone. So we can see that the nano network are very tight versus the frac zone is way more permeable. This whole device right here holds a few, like around 10 nanoliter of samples in total, where the enhanced oil recovery design holds a few microliters of sample in total. So we can see that great difference between, for example, core flood versus our device. And in the flowback test, we'll inject the flowback 8, which is a chemical, shown as blue here, into oil saturated preconditioned reservoir analog. And we let it soak for a period of time. Afterwards, we will flow oil backwards from the reservoir side into the frac zone. This kind of imitate in the field where you inject chemical downhole and withdraw oil from the reservoir. And the straight channel shown in this image is what we call it volume accumulation channel. We will use these to illustrate, to visualize how much oil come out of the reservoir, where we can measure the oil recovery factor. So that's pretty much it for me. Next, I'll turn the slides to Dave, who will show us how Interfaces technology enables safer operation.
Thanks, Kara. Okay, so smaller samples, smaller volume really results in a smaller footprint. So in resulting in safer operations. So looking at our devices here, this is a lab footprint compared to our device compared to the core flood analysis equipment. And as you can see, our device is actually much smaller. This is for porous media, much smaller, can actually fit on the table over here in the traditional core flood equipment. Also, our PVT cell, this is basically our PVT cell. PVT cell here, your traditional, this is courtesy of Schlumberger, is 150 milliliter, 150 cc cell that's contained in an oven. You see a huge footprint here, a large sample volume. The sample volume of ours for this particular cell here, or chip, is, or analog device, should say, is about 0.82 microliters. Because of the small volume, there's very little energy produced. What this is kind of an energy comparison of everyday things. So the energy produced, or the energy contained inside of one of our chip, because it's such a small volume, is basically similar to the energy of lifting an apple off the table. It's actually less than that. The sample cylinder that comes from downhole is your typical 500 mil sample cylinder here. So it's much more volume. So of course it's going to be much more energy as well. And the worst case on this particular table here is your energy contained inside of a compressed air vessel. So looking at this compressed air vessel, comparing it to our chip, they have 170 liters at 70 MPa, which is about 10,000 PSI or 700 bar. Produces 65 megajoules, which is equivalent to about 14 kilograms of TNT. Ours is much lower. So basically ours is the energy required to lift an apple off the desk. We got this energy through this energy isothermal energy equation here. So that's how it was worked out for your compressed gases on here. So the next slide here kind of compares, this is 2 kilograms of TNT that's inside of a concrete block. It's a 1 cubic meter concrete block. So as you can see, you know, larger the volume, the more energy. I mean, which is just pretty normal anyway. Here compared to, and basically lifting an apple off the table. So really what we're trying to say here, because of this, the small sample volumes, our equipment is much safer, a much smaller footprint. Now with the analog, you still have to house it inside of something, as Kara showed on one of her slides here, the chip holder, analog holder, but it's very small compared to like a traditional PVT cell. As well, you have the supporting equipment, including valves, lines, fittings, and you know, other equipment that's a part of it, but it doesn't exceed 5 milliliters. Our full setup doesn't exceed 5 milliliters, which is far smaller than any core flood rig or PVT cell in a traditional lab, conventional lab. But despite this low energy, we still do our due diligence and make sure that it's safe to operate. So we have rupture discs in our systems, safety systems such as rupture discs, pump hardware clutches on our pumps, and plus software pressure control settings. We do have a high standard of QA. We test every high pressure device that comes in the lab. We do our QC. We have standard operating procedures. We make sure that everything all of our data is done the same way and to whatever the operating procedure is. Looking at the manifolds here, it's kind of getting more into the manifolds. We do have a patent pending on one particular manifold, a screw top, quick to load analogs, and this particular one can hold up to 350 bar. We also have higher pressure systems, but these are still in the confidential stage. But these systems are all designed to ASME and tested to ASME. And because these are so small, we can basically test them in a small chamber here. So this is just our standard toolbox that is lined with a 1/4 inch plate steel. And we can, because of the energy that's produced on that is so low, we can easily test it in here. Any larger volume system, you'd have to test it in a conventional pressure testing chamber, which is like a separate room, and you have to go outside of it. And also, we also test every piece of equipment to full operating conditions, maximum operating conditions, so temperature and pressure as well. So in conclusion, our technology is, well, smaller samples. That's what microfluidics is. It results in more convenient shipping, lower emissions and disposal implications, and leading to safer operations. So basically, it's easier for our clients and ultimately better for the environment because of the less solvent we have to use, and the less amount of oil that we use, which actually reduces the amount of sample that you need from downhole, which the samples that you get from downhole can run into millions of dollars depending on how much it is. And we only need fractions of what's required on a traditional conventional lab.